Hello, how are you?
So good.
All right. About the regression reports, some of you had used categorical variables without using them as a dummy variables, and that is totally incorrect. So please correct those to the final report. Final report, I I did put the last date for it. I think it was the last day of this month. But if I remember correctly, I sent you a news message from it so you can check it. Please remember that the final reports you will go through this Turnitin and it will check everything. It will check your grammar. It will check whether you have any kind of plagiarism there and so on. So those scores are also affecting your scores for the final report. Anything to ask about those things?
Does Turnitin check grammar?
Yep.
Okay. How severe does it influence our grade?
Uh, it's not a big thing, but of course, if it says that there are lots of mistakes, it may decrease the scores. You have a maximum of 10 points from the final report, so but it's at most 2 points. That is extreme case, the 2 points. So, but the point here is not so much that how much it's affecting to your scores now, but the point is that when you do your final thesis, you have to use it, and now you just get familiar with that program and what kind of information it's giving to you and so on. Yeah. So today we finally start going through numerical methods, and I take this from here. And everything what we do in last assignments, it's just acting with numbers. And like I told you earlier, you should return either Excel file to me or MATLAB file. MATCAT would be one possibility, but the emulator doesn't recognize it. No PDF, so it has to be XLS or the latest form of Excel, what this school offers to you, or mfile .m kind of case. So when I get the file, I need to go run it. So for example, in MATLAB, I open all the files in MATLAB and I run all the files. So you must be sure it's working correctly, because if I cannot run it, it's not working and it's almost the same as you haven't done it.
So, when is the deadline for this assignment? Because I couldn't see it in Moodle, and I thought we just did it for training.
I opened the interpolation extrapolation part today, so it's up to you. I think for the last day of this month, you already have a learning diary and a final report. So maybe you wanna return this after the Easter. Is it okay?
Yeah.
Right. And in the Excel, I will check all the functions you have used and so on. But also it's only the program what you are returning. You have to have the analysis of your result included. So in Excel it's not a problem because you can always have a text box there and write the text there. But in MATLAB file with the percentage sign you can get the comment lines, and with, inside those comment lines you can have your analysis. And like I said, all of them will be run. In programming, of course, the main point is about its working. If somebody is doing it extremely nice, I mean that the programming is quite sophisticated form, I will give more points. Although I comment your programming, it is just to give some hints for you how you can do your program to be more general, so you don't need to do so many steps in your programming. So it's not only as a negative and minus scores and so on. It is just to help you later. I had something in my mind what I was supposed to tell you about the program. Yes, if you use pre-programmed functions, in many exercises I have said which method you have to use. And if that function is not using the method asked, you will lose the points. Anything about them? Did I forgot something? Basically everything is clear to you. So the numerical method part, what we have here, consists of interpolation and extrapolation. We go through them today. Next time we go through the curve fitting part. And the last topics are numerical derivation, numerical integration, and differential equations. If I remember correctly, we have one lecture per week. So today we go through these two cases, but all the others we only have them one time one. These are here separated only because I wanted to separate these methods so that you can see the differences. But when we go through them, you will notice that they can basically be used mixed. So, some of the lecturing books talk only about the interpolation, and that includes also the extrapolation, and some of them talks about the extrapolation only, and the interpolation is included there. But they are different things. Although the algorithms may be about the same, but they are different things. But before we go to that part, the idea here is that despite what method, what is the topic, you always have several measuring points. So you may have been in the laboratory and you have to get values for different things. For example, at 5 minutes, every 5 minutes or every half an hour, and for several hours. So you can understand you have lots of data. Numerical derivation integration, exactly the same thing. So you have lots of data. And the amount of data is usually much more than with the statistics part. And somehow we should get information about what happens there. Interpolation and extrapolation is approximating the values. And when we were talking about the functions, for example, for a linear function, you understood that it's only 2 points you need to get a function exactly, because it's a straight line. It needs only 2 points. But now you have several points, and they don't usually follow some function exactly. They are close to that function, but not exactly. So somehow we should find the idea of what the function is, although the values are not exact. And for that reason, the first 3 cases here, all of them are somehow the same, but they have their own things what we have to think about. So we start with the interpolation. So interpolation is that, for example, if in this graph you know the value at 0 and you know value at this point, you have some values here in the middle, but what the point you want to know is not exactly any of them, but it's between these 2 points. And if it's in between, then we talk the interpolation. If the value which you are interested in is outside these points, so for example here, we talk about the extrapolation. You already probably understand how close these methods are and how they can be understood as a one. But to separate the idea of what is the interpolation and extrapolation, for that reason they have been separated also here. If you then, let's say, then you can go to the school library. You can go to the part where is the lecturing books for numerical methods. And you can open one or two of them, and you will notice that for this interpolation, extrapolation part, there are so many methods, and there is no point of going through all of them. Most of them are based on some form of a divided differences, but I want to go through the Lagrange method here just because it's very important in the numerical integration part. So we need it also later. On the other hand, it's a little bit different than the divided differences, and it may give you some idea of what happens. Here is the formulas needed for the Lagrange method. So this is the end polynomial you get with this method. This is the value you got in your measurements or somebody else got it, but anyway, it's a value you already have. And this Li is solved with this formula. And at this point, it may seem that this is quite bad and long, but actually it's much easier than it first looks like. As you see, here we have only the x. So this is the variable what is going to be here anyway. So it's just a variable. Here we have the measurement points. So for example, at 10 seconds, 0 seconds at the beginning, at 10 seconds, and we continue till the point. And if we are concerning the point, for example, at 15 seconds, this one would be the point previous, and this would be the one after, so the next one. And when we do these, so if you have n measurements, your polynomial would be what is it? Degree of n minus 1. Here, this is the value at the point you are concerned. So it would be the 10 seconds. And this would be the first value, second value. So you would get these differences. And denominator here is just a number. And this one would be the polynomial. So here is one example of this case. We know it follows this function, so that's why I have used this. So if we get the point, use the points x0, x0.5, x1, we would just put this to here and get the value. And as you see, we go in the order. In the first one, we don't use the first x value at all. So we only have the last two. X minus second times x minus the third. And because we are concerning the point, first point, xi is 0, so we have 0 minus half, 0 minus 1. And here the value, the measurement value, and in our case, e raised to that point. Same here, only is that we have excluded this. So we do it for this and this. And the third one, the first two. So we get a polynomial of degree 2. So we have a quadratic function here, quadratic polynomial function with the multipliers. And this is the approximation for our e raised to x case. If we draw the function as I have done here, you see we have our points here. We have with the red one drawn with our approximation case. We did have the first value at 0 and the last one at 1. And this red and black one goes nicely. They are not exactly the same, but they are very close to each other. At this part, it seems to be quite close, but we don't know, we don't see what happens here later. But at the left side, you already see that because we didn't have any values used here, they are going to go to the different directions already. So this function is going quite nicely. It's giving you good approximation if your x value is between 0 and 1. But outside the result may not be so nice. So that's why Lagrange is usually used for interpolation. Anything you want to ask about this method before we continue?
Not really. It's clear so far.
Good.
Yeah, well, will we reproduce the same method with MATLAB?
Yeah. If you use MATLAB, you should somehow get this one program there.
Okay.
It's not so bad as you think. Yeah. Divided differences are it's easier method in a way. It's shown here with the Excel only because I wanted to show you how it is formed. I haven't written the functions and formulas in the same form as with the Lagrange, because I think this table tells you a little bit more and it's much easier to understand what happens there. So here are our values, the points of measurements and the values at these points. So if we go through this example at the same time, the function what we have been checking at this point is exactly the same, but at this time we have 4 points. So at 0, 1/3, 2/3, and 1. So those points are given here, and if they are used here in the function, these are the values we got. And it says here that the next step is to solve the difference between the values next to each other divided by difference between the variable values. So here 1.39 and so on minus 1 divided by 0.33 minus 0, and you should get this value. Here it is done for these. Okay, I cannot show it to you. And for this one it is done for all these. When this has been solved, we go further. So we do it for these and these. So the difference of these values. But because here the point used was this one, the maximum point, and here the minimum point used was this one, so it's a difference of these. This one and this one. And here, denominator is this minus this. And the last step, this divided by 1 minus 0. And you get this one.
So I kind of missed it. Do we have 3 different functions in the upper table, or it's the same functions but with 3 different arguments? Because it's F1, F2, and F3, and I'm confused whether those are like separate functions or
let's see. I try to draw here. So I use my mouse. So if it's not working. So if we are checking this value here, it should be, if somebody has the calculator, 1.395, I don't write all those values, minus 1. So it's the difference between these two. And then difference between these. Is anybody had time to check that it actually is 1.18?
So it's just a value for y. So it's basically the output of function. It's not 3 different functions.
No, it's not the 3 different. It's only.
It's for 3 points, if so to say.
It's just the next step in reforming the polynomial function approximating the case. So yeah, I got the same. So if we are checking this value, it should be 1.65 minus 1.86, and here it is the difference of 0.667 and 0. And the next one should be 2.31 minus 1.65 divided by 1 minus 1 of 3. So we get this value. When we have all this, we have gone till the point where we only have 1. We can do it as a forward method, or we can do it as the backward method. If we do it as a forward method, the idea is that we start from here and continue to this direction. And we should get the function. Okay, maybe I just use this eraser form because it's just. So as you see here, it says take the original point of the starting. Here we have the 1, it's written here. Take the next value at the next step. So take this value times x minus x value at previous, plus the next step, and we do this x minus the x values for all previous cases. So for this one and for this one. We take the final value and we do the differences for all cases. If this one would be simplified, what I haven't done in here, you would have a quadratic polynomial function to approximate EX. And that would give that at point 0.5, the value would be about 1.6482. If we check it from here, okay, it's not given here, but you can put it in your calculator and see how much it's how good or bad approximation it is. So in forward method, we go basically down this one, but in the backward method, because usually this is written in a triangle form, but it's not so easy in the Excel. Oh, okay, it's easy if you have the extra empty cells there, but I didn't use space. It would be starting from here and going upward. So it looks like that we are going with the last line only, but exactly the same case. So here we only the point with 2.3, which basically would be at this row if it's in triangular form. So one point we already gone through was 1, so it's x minus 1. And we continue in the same way. And then we get the backward approximation, and in this case they give exactly the same value, at least with 4 decimals. I don't know what happens in the 20th decimal, but it doesn't matter. It's close enough. Any questions?
No, not really.
Okay. So these are here in the interpolation part. I will go through also the extrapolation because it is so close to this one. There are a little bit different kind of methods, but like I told you previously, they are in a way used also as an interpolation method. Gregory Newton's backward method, this is, okay, let's say Gregory Newton's method is the only one which I am just thinking is there any sense of using it for interpolation. Because the idea here is that your the point what you are studying is outside the interval what you have. So for example, if here we have we already know the values at 1, 2, 3, 4, and 5, and we are concerning the point 5.7. Our age would be 0.7 because we are outside the interval uh, for that. I'm too tired. So anyway, the difference to the closest actually known point is just 0.7. Although this is given as a backward method, but the same case, you could use also these, and you have this kind of forward method to what we had here with the divided differences. The divided differences, how to get this table was a little bit easier because you just took these values. Here, basically the same thing, same case, but as you see, it's given in a formula form and it looks a little bit odd, but it's just telling that get these differences. Gregory Newton's method, I have checked this one several times, do not have any dividing here. So when in with divided differences, you were always dividing this difference between the difference of these, but in Gregory Newton's formula there is not that kind of case. And I said I have checked it several times because in many cases I have seen that they talk about the Gregory Newton's method and they are dividing it like divided differences. So I haven't understood yet whether it is just a different kind of a form of Gregory Newton's. Did they confuse the different methods or what is going on there? So I am quite sure it's just a different kind of form of this one. Like I said, there are so many methods, and I think at some point everybody wanted to have their own method because it was so easy to get these. Here, the example is for this kind of function. So these values are solved exactly with this. And now we want to have approximation for this one. This is not linear, it's not a quadratic because everything with the variable is in the denominator. And this will give us some kind of a polynomial approximation for this function. And as you see, forming this table is easier compared to the divided differences, but forming the actual function is not so easy. So it's just 25 minus 100. 11.1111 minus 25. Same here. This minus this gives you this one. This minus this gives you this one. So we get the point. And now because our point 5.7 is here, we go the backward method. If we would be concerned about, for example, at point 0.7, 1 is the closest and we should use the forward method. That's the only difference between these. So when we have all these known, we go back to this formula. So for first one, the actual measurement value, when it says that here it's in a little bit different form, it says 8 times the differences of those f values. So our h is 0.7 and the value here is minus 2.25. Next one, we are here. So we take this value, which seems to be 2 point, this is something needs to be checked whether this is 2.26 or do I have a writing mistake here? Probably here. But anyway, it is this point times h times h plus 1 divided with this one. And we continue at the same time, same way. All the way, all these values are done. So it gives us that at 5.7 approximation for this one is 22.95. If you substitute 5.7 here, you will get exact value 0.787. And this tells you how much in the extrapolation approximation can differ from the correct value. So in the extrapolation, it actually is the approximation and not always even a good one. What would help here, that if we would have done the scatter dot of this one, like done here, you see it's going like this one. So it's going like more like the exponential function or something like this. So this doesn't remind of any polynomial function, and that tells us that this polynomial function is not good here at all. And for that reason, we have this next topic here. Because with the logarithms, if you have something here as the power, you get it outside. So if we take logarithms from both sides, these exponential cases, they start to remind more linear function. So we do the same table, but we have the logarithms from our x values. We have a logarithms of our measurement values. And when we start doing the table, you see at the next step, value is minus 2 in each of them and 0 in the next one. So there is no point of continuing because they would be 0 already. And because we could go only to one step forward, we already know that the logarithm form is actually a linear function. So you could use this one to get the approximation function. When you get the values for this one, please remember you have to take the logarithm from the 5.7 also. And the difference between this and this is this one. So you do the approximation function for logarithm values and you get the approximation from there, and then you get the approximation for the original 5.7. Any questions now?
No questions.
Okay. I have shown here also divided differences. And as you see, we have a lot of values. So this looks more like our actual measurements in the laboratory and so. In these kind of cases, if you have a possibility to use the interpolation methods, use them. But here I have just wanted to show to you the extrapolation how it can be done. If I would be doing this one as the actual research, and for example in here I have been concerning the value 4.463, I would have taken some of these values so that this one is somewhere in the middle and used the interpolation idea. But this is now for extrapolation. In these kind of cases, you don't usually need to use all the points. Just take, if you have a possibility to do this scatter dot like I have done here, you get some kind of idea which kind of polynomial function would be quite good. And that tells you that, okay, if it looks like a quadratic, take 4 points. If quadratic, take 3 points. If it looks cubic, take 4 points. In the extrapolation with the green one, I show how it's done with the backward method, and with the red one, it just tells you how it's done for the forward method. I have done this table to all points, but and I did do it with the Excel, so I haven't taken these values away. I could have done it, but I didn't do it. So these values here in the triangle basically are the ones we don't need at all. Green one is the backward method because our point is a little bit more than 4.4. Red one a little bit yeah, and the red one is forward method because our point is a little bit less than 4.5. But basic idea, we start doing it, we take this one plus this times and what was done there in previously plus this times what was done. These functions are formed in exactly the same way as they are done in the previous one. You can also see them here. Functions in this form looks a little bit different. The values they give are a little bit different, but if the first difference is in the fifth decimal, it's not affecting at or at all in this case. What is very important here is that when we solve this one, you see in the third step, they are quite close to zero. And in normal cases, the previous examples were these nice math lecturing book math cases where everything happens to be so nice, but in normal life they are not so nice, but they just end. So when you see they are very close to zero, you can just say, I don't continue anymore. If there happens to be so that this one would be, for example, almost minus infinity, this one would be almost plus infinity, you already know that it's not going to end anyway. So in that case, I would say either you just stop it and you try to get some approximation function, or you try to find a better method, because not all of them are using divided differences. So basically, this is how you get the functions. When you have the function, then you can do the approximation, either for interpolation or via extrapolation. And I think I have to open your next assignment. So you actually know what you need to do. Uh, when do you want to have a last returning date? When do you want to return this one at the latest?
Well, I think we will be okay if we return it after learning diary and the last final report.
Uh, are you going to celebrate Easter, or are you going to study?
This is a good question, though. I don't know. Maybe.
Is it a 7th of April? Okay. The problem here is that this one shouldn't take so much time. So it may be that you have done it already today. But because at the end of April, I'm going to be basically in Portugal and in Tallinn, of course, via Zoom, but anyway, I do not have time to have your lectures. I would like to read and give points from most of your reports before that one. So if I put this one for 7th of April and the curve fitting, what we are going through next week, at the same week on Sunday, because basically they are almost the same things what you are doing, so they are helping each other. Does it sound okay?
Well, yes. So my question is about the final report. We just compile all previous reports into one big report and basically do not add anything.
Basically, you should add there so much more text. So your final report should be like your final thesis where you explain everything what you wanted to study there. So the the reporting part, what you have done now is just you get the results, and I checked that you can get correct things and you get use the correct variables. And now you should form it as one report which is logical and makes sense. Of course, if you want, you can change also what uh, uh, tables you have. So if you, for example, find out that your hypothesis test for one distribution case is not giving anything for your report, you have selected a not so good variable and you want to run it again, you can do it, but you don't need to do it.
So we need to add more text explaining what
Yeah,
analysis is.
it
And
depends. It depends a little bit case because some of you have already written a lot. Some of you have just basically returned the tables. So if you have returned only the tables, you have to write down the text and explain. If you have returned the text, you are in a good way. But now you have to combine all of those reports so that they look like as one report and not as what you have put three different reports together.
so, well, I still have two questions.
Mhm.
First of all, if you in I think most of the reports you had the criteria called analysis, and is it what you mean by text? So,
Um,
or we need to add more analysis
let's see, do I have
because
this? Yeah, what I want, this is just kind of a report and although it's in Finnish, there is no statistical things done here, but like here, it should look like a report. So you have a text. In numerical part, you don't need to have so much text. It's more about programming. But in statistical part, it should be more like this than just tables. This
okay,
is
so
not, yeah. Yeah, ask.
it is a combination of learning diaries where we explain the part where we explain what we actually studied and what the
No,
idea.
learning diary is just what happens in your head. But with a report, uh, for example, here, if we go through one, uh, where is the introduction? Why this is done? What is the situation at the moment? So, for example, in your case, you can give in the introduction why this report is done. Did somebody ask you to check the prices of apartments and so on, or whatever is your case, and when? What you can figure out, for example, about the uh, uh, correlation between the variables and so on. So it should go in the logical form.
Well, okay, I more or less have an idea now.
Yeah, good. And these final reports cannot be redone. So it's just if